Hello friends, hope you are having a fantastic day today. Now in the last two sessions we learned that what system design is and why does it matter. Today we are going to go deeper into the key concepts of system design. So concepts such as reliability, availability, modularity, fault tolerance, scalability, and bunch of different cool concepts. So in my opinion, this video is going to be really impactful and really informative. I hope you find it useful. Now let's get started with our first key concept. So first concept we are going to talk about is going to be scalability. This is a really important topic for any system design that you are planning to design, that you have to understand that whether system is scalable enough or not. Now, what does scalability mean? If we see the definition of scalability, it simply defines that it is the ability for any particular system to handle the increased load efficiently without having any issues and without having any impact on the outside user. So say for an example, if this is your Instagram system, right? Now we all know Instagram is one of the most popular services out there. Now initially when Instagram started, it only started with few hundred or few thousand users. Let's say that there were 10,000 users who are using Instagram and they were able to use it efficiently. But sooner or later, Instagram became more and more popular, and now currently billion people or more than that actually use Instagram. The thing is, even for these billion people, Instagram is still behaving the way it should, which means we can define that Instagram is handling the scalability principle, or the system that Instagram has is actually scalable with the increase in the user growth. Now, question is, how do we actually achieve scalability? We all know that if we have any particular server or any particular computer where we are running our system, basically what would happen is that, let's say your application or the number of users who are calling your server keeps on increasing. So what would be the first thing that would come to your mind? First thing that would come to your mind is that, let's say this computer is currently 16 gig in memory, and it is, let's say, 1 terabyte in SSD hard drive, something like that. These are the configurations, and you see that there is a rise in the number of users calling it. The first thing that would come to your mind is that make it a bigger, better, stronger computer. So what you would end up with is you are actually going to have, let's say, 32 gigabit RAM, then you are going to have 2 terabyte memory, then you are going to have graphics card, something, and then your system would work fine. This is what we typically all did when we wanted to play higher versions of Call of Duty. That we would just buy better gaming PC, and our PC would be able to accommodate the new version of more powerful games. So this, what you are currently doing is that you are increasing the scale of the existing computer, which means vertically we are going higher in the capability of our system. That is defined as vertical scaling. Now this is a really important concept, because many times all you need to do is just increase that available number of computers you have to grow them in a much higher capacity to handle higher amount of load, higher amount of user, or higher amount of system traffic. So vertical scalability works perfectly well. But we all know that there is a limitation of the only number of high we can go vertically. So what would be the next solution is to have bunch of different similar computer. Let's say that you kept going higher and higher and higher, but eventually you ran out of, let's say, RAM to be 128 gigabytes, and then you have 10 terabytes of memory, and you have like the best graphics card in the world. Still the number of users are keep on increasing. What would you do then? So the next approach would be to go horizontally, and that to have a number of the systems that are similar or different to each other talk with each other. So what would happen is that the number of users who are calling, let's say the number of users they are calling through a system that looks like this, that was originally this version over here, but in the back end this system actually calls all of these multiple computers to do all the computation. Let's say you take care of all the networking bandwidth, you ensure that the latency is quite low and all the traffic gets routed and all the requests are being completed successfully, and then you return back sufficient answer to the growing demand of the number of users. In that case, you are increasing the number of computers you have, and of course you can also so this increase would actually define as horizontal scaling. This is also very important in the system design, that you need to increase horizontally. Now the question is when to use vertically and when to use horizontally. in my opinion, it's not going to be either one of them. In most of the cases, with the increased load, you also need to increase the capability of the existing computer, so you are going to go higher in the vertical, and with the increased load you might have to add some more computers to your existing system and have them talk to each other in the most efficient manner. So that way all the calls get routed properly and your users are able to use your system flawlessly. So this is a key concept of horizontal and vertical scaling, what it means. Now don't think that scalability is easy to achieve, because if it would be, then we would have like 10,000 Netflix or 10,000 Facebook like companies. These things are really challenging to manage that. And why it is challenging? Because let's take for an example this previous scenario, where we actually currently have 6 different computers speaking with each other flawlessly to complete some requests that are coming in from the users, and the number of users, they keep on increasing, and there are like millions or billions of requests happening every single day or every single hour. So the first thing that would first challenge would be to have the same response being sent by all of these computers. What it means is that many times in the system you are also going to be dealing with data. So what would happen is that for your existing system you will also have some database where you are storing some value of the customer, and let's say all of these systems, they are connected with this database as well, and whenever you need, you are able to get some appropriate answer. But one potential challenge would come in places that, let's say currently user 1 has the name as Parth, so I'm going to mention the name as Parth. Now this user 1 decides that I want to change my name from Parth to, let's say, Hinal, that is my wife's name. Okay, so now I need to go to change the name to Hinal. I send out a request to this system. This system randomly calls any one of the computers. So let's say it calls this computer, and now this computer has updated the name as Parth. But the thing is, all of these other computers, they are still connected to the older instance of this database, and immediately before these computers can get notified, let's say I want to change the name again, something else, to, let's say, Tana. Okay, so if I change the name to Tana, again I make the call to the system that, hey, what is the name? So let's say this time system came over here, and this system wants to fetch that what is the currently name saved in the user database. So in the user database, this system does not know that this computer has changed the name to Parth, and after Parth, let's say this computer also changed it to Tana. So it is possible that this system, they might give us back the answer of, let's say, that it says that this is the name is Parth or the name is Hinal. Meanwhile, the actual name is actually Tana. So this is a problem occurs when you try to manage the states across all the instances. So number one problem with the scalability is that state management, that you need to make sure that all the states are being same, and there are no issues with that. I'm sorry for butchering the spelling, but you got the idea. Now second issue that comes in is the load distribution. Why load distribution is the issue? Because let's say that you have 15 computers running parallelly with each other, and your service is sitting somewhere on top. Now in your system currently, let's say you have put the load distribution, but for the load distribution, the hash you use is not very good. Like the plan you use to connect these calls are not very good. What would happen amongst these 6 individuals? Let's say that only 5 gets called every single time, and because the algorithm is set in such a manner for this load distribution that this server never gets called, what would happen is that all of these computers, they would keep on running out of memory, and this is going to stay idle, and this is going to be bad for your overall efficiency of your system. So load distribution is another issue with scalability. Third issue is the data sharding, and data sharding is actually quite complicated, and I wanted to talk about this later, but let's just say that same way we have great multiple computers speaking with each other, same goes for database, that we are not going to have one big database that is connected all across. There would be multiple versions of database, and there would be different data being stored, or the partitions of data being stored in each of the database. So suppose it could be possible that we put down the condition that if the number of users alphabet starts with, like, let's say A to P, then store it in this user database, then P to, let's say, S, store it over here, then S to, let's say, V, store it over here, something like this is our algorithm to dictate that what the database should store. Now let's say that currently a person named Beta decided to make changes, so that change is going to reflect over here. But again, after some time, this beta actually changed its name completely to Sally. Now the name is Sally. Sally makes change, that change should be reflected over here, but we still have the older version of beta that has some change being stored over here. So now that this becomes the inconsistency amongst database. So again, it becomes tricky to manage the number of database with the increased scalability. And also even for this database, we also need to have scalability implemented in them as well. Why? Because we don't know that when the number of load is going to increase, and we might have to increase the number of instances of database as well. So there are a lot of issues. If we want to take best example of scalable system, we don't need to go much far. Let's take the let's consider the example of Amazon, because in Amazon typically it deals with large number of data. There is no issues with that. But let's say when we have Black Friday coming in, or we have Boxing Day coming in, the number of users that are going to be using Amazon is going to be double or triple in the same day, and that puts a huge amount of load on the Amazon servers. Now what happens if Amazon server starts crashing during these days? Of course, these users, they are going to have bad experience, and Amazon is going to lose ton of money. So that's why Amazon has to ensure that their systems are scalable, and they are able to handle the increased load efficiently. So this is quite important key concept for distributed system or system design. Now let's move on to the next very important system or concept, that is called modularity. Now I already talked about modularity a little bit while I was explaining that what does the scalable system mean. What I mean by modularity is that your system or your application has to be broken down into various modules. Now if you want to go and understand the definition of what modularity means, modularity typically refers to a design technique where you are going to break down the system into smaller and smaller fragments, and have those fragments talk with each other, rather than having just a one huge big machine or big system that deals with every single time. What would that in turn mean is that every single system or every single component is tasked to do some different functionality, and that functionality is independent of other modules. Now if you want to understand modularity in the best and most logical manner, try to understand the example of a car. If we see a car, typically a car has bunch of different things. A car has an engine, a car has different tires, a car has a tail light, a car has some doors, a car has some windows, a car has wipers. A car has hundred or thousands of components. Why did the manufacturers decide that the car is going to have all of these many thousands of components, and they all are going to work harmoniously with each other to keep moving forward with the way car is intended to be, and keep going smoothly on the road without having any issues? The reason is quite simple. Let's say if the tires broke or tires go flat, you don't want the entire car to have malfunctioning. All you need to do is indicate that your car tire pressure is down, or your car tire has gone flat, and all you can simply do is just open your trunk, get a spare tire, have that spare tire installed, and then keep moving your car again. What this in turn does is that it increases the maintainability of your system. So your system is easier to manage, it is easier to maintain, it is more scalable in a way, where tires, let's say, are going to have more load. You only need to increase the tire capacity or tire size, or just change the tires, rather than changing every single component of the car. So modularity and scalability, they work hand in hand with each other. Same way, it increases the collaboration. Let's say that you decide to go to a mechanic or something. That mechanic can be specialized for different components of car. You can have a tire shop dedicated only for tires, or you can have a paint shop or dedicated for only for painting, or you can have let's say a mechanic or some dealership that only deals with engine failure issues. And you can have different parts or different components being managed by different people, and they can keep working together to maintain your car in the best efficient manner. So these are all the benefits of modularity. Now let's try to understand modularity with accordance with our system design. So what modularity defines is, one of the key example I can give you is let's say the example of Netflix. Now in the Netflix, we all know that Netflix is typically a movie streaming service. Now in the movie streaming service, what is going to happen is that you are going to have your user come in, open the Netflix portal, that music is going to pop up, and at the same time Netflix is going to show them the options that, hey, these are all the movies, you can pick what movie you want to watch or what drama you want to watch. There are a lot of thousands of options available. But in the behind the scenes, Netflix is what going to do is that they are actually going to have a service that shows this decision tree. So let's say that there is this service that shows decision tree. There is also one more service that has this huge database, where in the database they are going to have all of these movie files being stored over there. So let's say that there is one more service that speaks with the database. There is also one more service in between that takes care of what user is watching right now, because they want to use this data for the future purposes. So again, since it is dealing with a separate database, there is a separate database for that as well. Same way, let's say that the user wants to upgrade their plan. So if user wants to upgrade their plan, there is going to be a separate payment services. And this payment service is also going to have its own database where it deals with that what user is watching what movie and how to connect that. Plus this payment service needs to somehow connect with the user's bank and through or their credit card, and then get the payment from there. Once the payment has been received, make an updation in the payment database, and then have that added like version of Netflix being shown to user. So you see how many components are speaking with each other in the behind the scenes, and they are all spread across modular without even user knowing that this is all of these things are happening in the background. So that's why modularity is very important concept, and you will see tons of examples when we go through this entire topic of system design and this entire series, because this is the bread and butter. You need to have a modular maintainable system in your application. Now let's talk about some more examples or some more key concepts. So next key concept is actually availability. Sometimes this is also referred as reliability as well. What reliability and availability means is that you need to make sure that your system is available or readily reliable whenever you want to. What it means is, no matter what happens in the background, no matter there are let's say some earthquake happened and your entire data server has crashed, do you still want your services to run as efficiently as possible? And let me give you a great example for this. Actually Netflix is pretty famous for creating something called Chaos Monkey. And what Chaos Monkey does is that it tries to see, or it tries to replicate that how would Netflix behave in a chaotic situation or in a chaos situation. So the funny thing is, with Netflix, they are completely based on Amazon Web Services. It's a cloud computing model. We are going to talk about that in the subsequent videos, but try to understand it for now. Now for this AWS, actually Netflix has its region located on 3 parts of the earth. So let's say that this is our earth. Now these are the 3 different regions where bunch of different Netflix component or Netflix applications are running. They are all modular, they are all scalable, they have their way of configuring all of those things, and plus they can provide suggestions based on geography. So let's say you are residing somewhere over here in India, and let's say this server is currently closest to you, then this server is going to show you more like India based data and whatnot. But some reason, global change or global warming or climate change, something happens, and let's say one of the server completely gets destroyed. I'm not even talking about the few computers crashing, it's just the building has blown up. What would Netflix do? So Netflix, they already have a system in place where if something like this happen, they are going to have the other 2 servers be capable enough to keep on showing the Netflix without any issues. And this is the best definition of availability, that how long or how for what amount of time your system is available or reliable. So for that you need to make sure that the systems are redundant. Over here we can see that the Netflix systems are actually redundant because they initially had 3 instances of same thing running on 3 different parts of world, but then one goes over, so again they are still able to function in the most effective manner. Again, once this got destroyed, automatically the load started being transferred to these ones, so which means they also have the failover mechanisms in place as well. that in case of a failure, just start routing the traffic to a different data center and have it running as efficiently as possible. At the same time, they also have a situation, they also have some, also at the same time, all of the applications, they are currently geo redundant, which means they are spread across on the different geographies and different areas. So if one part of the world gets affected, it is very unlikely that all the other parts are going to be affected as well, unless there is a like asteroid comes in that killed all the dinosaurs. If some kind of event like that happens, then only, I don't think then anyone is going to be interested in watching Netflix. But anyways, so you get my point, that what availability and reliability means. Now typically, in order to measure availability and reliability, there are these nines that are being used. So what these nines being mean is that, let's say this one is 99.999, means this is typically referred as 5 nines as well. What 5 nines means is that in a single year, typically you expect your system to be up and running or available 99.999% of time. This is one of the measures to measure that how available your systems are. There are a bunch of different concerns. There is like 99.99% as well, 99.9% as well, 95% as well, and different availability of course comes with different decisions and more scrutiny. So the higher availability you want, the more capable your system needs to be. So that's why for many services it is okay to have lower availability, because if they are not so critical. So let's say if we talk about again Netflix point of view, Netflix, let's say that there is one service that shows the previews of all the movie that you scroll through, and that preview is going to or is talking to some service in the background. Now for this preview mechanism is not that important to Netflix, rather than the ability to be actually be able to see the movies. So let's say that seeing the movies, they would try to target 99.99% that yeah, you should be able to see the movies 99.99% of the time of the year. But let's say for this preview series, you can you can be adjustable, and you can say that even if we are able to see it 95% of the time, we are still okay with that. I mean 95% is really bad in terms of availability, but I'm just giving you example so you can understand that what I mean. So there are a lot of considerations, but essentially you want to have a readily available system that you can rely upon, and many times this can have major consequences in terms of is it going to be a good experience for your user or a bad experience for your user. So you always want, whenever you are designing a system, you always want to make sure that your system is readily available and you are taking necessary measures to have that availability in place. Now let's talk about load balancing. I know we already spoke about load balancing a little bit at the beginning, but load balancing is essentially the art to distribute load across the multiple instances of that service. So let's say in this case, currently there are 3 instances of this service. This can be anything. This can be a database, this can be a microservice, this can be a Java application, this can be a cache, there can be 10 different things, but overall the load balancing concept is going to remain same. What this means is that currently this load balancer, it will know that all of these services, they are up and running. So for that, it will probably do some health check, that it is going to send out a message every single like 1 millisecond to make sure that whether the system is up and running or not. At the same time, it knows that okay, currently it has 3 different instances available, which means in its server it is going to do some hash calculation. Typically there are various hash that deals with the load balancing. So for understanding, let's just say that currently this load balancer knows that there are 3 different servers available. Whenever any service comes in, I can send it to first service, I'm going to send it to server number 1, second service I'm going to send it to server number 2, and third service I'm going to send it to server number 3. Now when the fourth service comes in, it is going to send back to the server number 1 again, and this is how it is going to do it. Now this is one way, this is a hash where it determines that how it is going to send the service to the backend. Now in my opinion, this is a very bad hash, and I'll tell you why later subsequently in this video. But first let's understand, coming back to our load balancer. Now this load balancer is actually dealing with these 3, and it is continuously checking that what is the health status of this. Let's say for some reason the amount of load increased. Now you already have a scalable system. So what this scalable system is going to do is that it is going to have one more service available for this load balancer to run, and that is going to be an instance of these three existing servers. Now this load balancer has four options. So again, the next subsequent service, it will start routing to these servers one by one. What would this mean is that load in theoretically needs to be equivalent. So there would be 25% load being distributed to every single server without any issues. Now this load balancing technique works as expected, no issues with that. But you need to have a load balancer in place that not only sends out the traffic blindly in the round robin fashion, but also takes care that all the underlying servers that are currently connected, how capable they are. Which means that it could be possible that, let's say that this service server number 2, or this second transaction that came in for this particular server, that was quite huge. And what this does is that this drains, let's say, 80% memory of this particular server. So now this server is functioning as at 80% capacity. Meanwhile, these other servers, they are functioning at, let's say, the 30%, 25% and 30% capability. Now because this is functioning at 80% capability, what would happen? Okay, first request came over here, second request we all know it came over here, third request came over here, and fourth request came over here. And now the fifth request is again coming to this first instance, but sixth request is also coming to this same instance. What this effectively does is that it could be possible that this was already 80% down in terms of its capability, and now it's almost like 99% down, because there is one more request that it needs to solve. Meanwhile, we still have the other places where there is a lot of capability left. So in my opinion, load balancer should also consider that what is the available capacity for the subsequent servers where it is distributing the load. So there are a bunch of different techniques available. There is like round robin, there is least connection, there are a few other like hashing technologies. You don't need to know every single thing about load balancer, but you have to understand some basic concept, that if you have your own load balancer that you want to implement, how you are actually going to do that. Now comes the important topic of caching. Now cache is quite important and very interesting and used every single place very highly. Let's take an example for, once again, Twitter. Okay, and now Twitter is being called X, so let's take an example of X. Now on the Twitter, one of the popular account is, and one of my personal favorite account is CR7. Cristiano Ronaldo 7 is a very popular account. Now we all know that CR7 is being followed by probably millions or billions of people all across Twitter, and any single Twitter post this CR7 makes, this post needs to reach to the feed of all of these millions of people. Meanwhile, there is one more account over here, and this particular account is actually, let's say, of me. While I'm not so popular as CR7, and let's say I only have 30 followers. So whenever I make any single post in the X, essentially that post needs to go to these 30 people. But meanwhile, if CR7 makes the post, that post needs to go to all of these millions of people. Now in my case, what would happen is that amongst these 30 people, maybe let's say 10 people, they are going to retweet, or they are going to do something with that. But it is very likely that in the CR7's case, amongst these millions of people, at least let's say 1 million people wants to repost or retweet this tweet. So what would happen in the retweet scenario? Let's see behind the scenes. If I take an example for my tweet, okay, currently my tweet, I posted it on the Twitter feed. So on the Twitter feed, my tweet is being shown over here. What is happening in the background is that my tweet is also stored somewhere on the database. Now in this database, whenever, let's say, one of my friend Harsh, that friend wants to retweet my tweet. So what this process would do is, it would go to the database, fetch whatever I have tweeted, and then post it on Harsh's feed. And on this Harsh Twitter, it is going to show that Harsh has retweeted my tweet. This is going to be the simple logic. Now let's say the scenario of CR7. For Cristiano Ronaldo, millions of people are seeing his tweet in their Twitter feed. Now all of these, amongst these million people, 1 million people decided that they wants to post this retweet. So should 1 million people needs to go to the database and have that tweet again coming back to their profile and then again being shown in their Twitter or X feed, that is going to be really bad system. Why? Because in this scenario only 10 database calls were being made, because I'm not that popular and I'm only seeing 10 database calls being made to the Twitter feed. But in the Cristiano Ronaldo scenario, there are 1 million database calls being made. Now, if you know anything, database calls are expensive. So there is a mechanism called cache. What this cache does is that cache resides in between database and the server, and cache is actually designed for fast interaction with the services and also fast interaction with the database, but it is expensive. Of course, you cannot have good, cheap and fast all at the same time. So again, this is pretty fast, this is really good, but this is also expensive. Database is really good, but it's not fast, but it is also very cheap. So you see, there are trade-offs being made over here. So what trade-off we are going to do in the Cristiano Ronaldo's case is that his tweet will be stored over here and also at the database level on both sides. And at the same time, if any of the million people decide that they wants to retweet what Cristiano Ronaldo has tweeted, they simply need to go to this cache, and cache is going to provide them the data really fast, really quickly, and then it will start showing up in the Twitter feed. Now let's say after 2 days the people are no longer interested, and then they can the Twitter feed learns it over time that how to do it and how to handle it. It realizes that now people are no longer interested, so let's just get rid of it. And so what they would do is they would delete that Cristiano Ronaldo's tweet from their cache to make room for other systems, and still the Cristiano Ronaldo tweet is going to be stayed in the database. So this is how the combination of caching and database is going to be very interesting for the user. Now let's talk about data consistency. Now what the definition of consistency is, that whenever a change is being made for any single database, that change needs to remain same all across way. So going back to our previous example of names being changed. Now let's say that currently this is the Facebook service. I am a user of Facebook. Now as being a user of Facebook, currently my name is being shown as Parth Vyas. Okay. Now on the Facebook feed, I decided to somehow go ahead and change the name from Parth to, let's say, Popu, something like that. Okay. Now in the Facebook feed, my name needs to be changed to Popu, but again, Facebook is a modular system. It is scalable. There are a bunch of different components speaking with each other. Even for the database, there are millions of instances of database deciding. Now the name is being changed to Popu over here, but there is also cache in between. There are a lot of things. There is a least recently used cache. There is the most recently used cache. There are a bunch of different things happening in between. Now on my side, I pushed the notification that name should be changed. Let's say Facebook, they also changed the name on one of their servers, but other servers are yet to know that this name has been changed. And when I go back to my Facebook page, I'm still seeing the name as Parth Vyas. This clearly means that the strong consistency was not present. Why? Because this Parth name came from some other instance of the database. Meanwhile, one instance of database has already changed the name, or also it could be possible that it came from the cache. So how to deal with that? So one way to deal with that is that I'm going to once I submit that, okay, change the name to Popu, Facebook decides that it is also going to change every single instance of database where the name Popu has been stayed. And then once it is done, then only it will say that, okay, now your system is done, and now you can go back and start using. And now if I come to my Facebook feed, I'm going to see the name Popu, which means now all the instances has been correct name. But what would happen in between? Of course, the moment I submit that, hey, I need to change my name, I'm going to be I will have to probably wait 2 to 4 seconds or something like that. Meanwhile, this buffer circle is going down in the circle. I'm so sorry for my drawing skills, but you get the idea. And then once it's done, I will be able to do it. Now what this effectively did is that it blocked me for 2 to 4 seconds because the change was really critical. Now in this case, we are only talking about name change, but let's say that we are dealing with a parking meter system. Now in the parking meter system, whenever the moment you use your credit card and you are making some pay, you want to make sure that the payment has gone through, which means that the credit card company has agreed that yes, this person's credit card, we already make sure that it has gone through, it has gone to my bank details, and in my bank that money has been deducted before I'm being shown that yeah, now I'm able to get out and generate a receipt. So for that, definitely I need a strong consistency. But let's say there is a system where currently on the YouTube, there are the number of views that are being mentioned. Now for this views, do I need to have such strong consistency, or can I be okay if the number of views, let's say that currently there are 10 views and in the next second 1000 people watch, these 1000 views are not being updated immediately, but rather they do these batch jobs that would be less expensive to YouTube, and after let's say 1 minute it will show me that yeah, from 10 your views were actually 1000. Well, that's reasonable, that is acceptable, there are no issues with that. So again, when you are designing your system, you want to make sure that how much level of consistency you need. If something very critical is there, you want to make sure that the consistency is followed to the teeth, even though it at the expense of wait time. But if there is something not important, of course make sure that the consistency is lower and it is also acceptable. Now let's come to the next topic that is really important, and that is my favorite, and that is distributed systems. I'm going to make an entire video on distributed systems, what it is, why do we need it. But just to give you a brief idea, what distributed system means is very similar to horizontal scaling and all the other concepts we talked before, which means that any single load that is coming in, not only one single computer is handling that, but a series or sequence of computers or database, they are connected with each other in a grid like situation, and they all come together to handle that load and then provide the response back. And that this distribution is common across all the different cache. There can be distributed cache, there can be distributed database, there can be distributed applications, there can be distributed servers. So everything that we deal with, every piece of equipment, that is going to be distributed, and that is the key concept of distributed systems. So that is why it is really important to understand. I'm going to make an entire separate video on distributed systems, why do we need it, so you would be able to understand in more deeply. But any single application that we deals with, they are distributed system. Now one more important concept in the system design is security. You want to make sure that your systems are secure enough and viable enough. What would happen is, let's say that I create a company that is similar to Facebook, and I'm just name it as Pathbook. Okay. Now this Pathbook is very similar to Facebook. Now it is challenging that what Facebook does. Currently this is not so popular, and I'm able to, let's say, handle 100,000 services or 100,000 requests every single second. But what would some other malicious company would do? I'm not saying Facebook is going to do it, but let's say some other third party who wants to see my Pathbook go down. So what would they do is that I'm only able to handle 100,000 systems, but they are going to start creating or generating fake load through bunch of different systems, and they are going to make millions of requests on my application, and eventually my application would start crashing because I'm not able to handle this much load. So what this essentially did is that they did a DDoS attack, and essentially my services have gone down. So this was a security threat. What is one more security threat? Well, of course, the best security threat is that, let's say that rather than this being a Facebook, let's say that I am a banking system. Now in the banking system, I try to enter as person X, and this I'm not person X, but I try to presume that I am that person, and then I try to gain access to their system, and once I gain the access, I essentially wants to drain out all the money. So what this bank has to do is it has to make sure that who is claiming to be person X, is that correctly person X or not. So there are a lot of systems in between. There is a user ID and password, then there is also that what is the location, then there is also authentication based on some like two-factor authentication, then there is also some authentication based on the device they are using. So there are a bunch of different consideration, and also that what is the firewall or what is the IP address they are using. So a lot of things bank has to consider before giving access to this person X to their system or to their accounts. So this also comes under the umbrella of security, where you need to start thinking about things like how to implement two-factor authentication, how to implement single sign-on, how to start implementing, let's say, OAuth 2. So we are going to have a whole different session on security as well, because it is paramount. No matter how stable situation is, if they are not, if your services are not secure, eventually this is going to be a huge downfall for your application. Because let's say that this bank has a major breach, and let's say that over 10,000 people's account information now they are available on the dark web. What would happen then? This is going to kill that bank's stocks, because immediately next day in all the news channels you are just going to see this detail. So these are all the concepts you need to take care of and you need to understand. I know I kept on going on and on and on in this video about various aspects and various considerations, but system design in itself is a topic where you have to think about all of these things, and that's why we are going to make somewhere between 75 to 100 videos on the system design topic, and we are going to go deeper in every single one of them. So don't worry about it. I hope the purpose of this video was just informational, and I hope you gain some insights.